We are going to look at the integration values that we find in a proton NMR, and we're going to start with this bromopropane. And let's first look at how we get the peaks, just as a refresher. If we look at hydrogen A, or proton A, it's described by this triplet over here. So why is it a triplet? We get one signal for each of these, right? So even though there are two, there's only one type. So we get a single signal. But we see that next door in the adjacent carbon, there's two hydrogens labeled B. So we would take one for this here, this type, plus two, and so that gives us the triplet here. For B, we have one signal for type B, but we also see that on the side here we have two hydrogens labeled A and a total of three labeled C. So that's 3 and 2 is 5, plus the 1 gives us 6. So that peak here is 6. And finally for C, although there are 3, we only get one signal for that type. And then there's only 2 next door, so that gives us a triplet. But now what we should talk about is called the relative abundance or the integration, because when you have proton NMRs at the college level, you're going to see these values here. If you look here, we have for hydrogen A, we have 1, we have a B with a 1.03, and then a C with a 1.49. In calculus, integration means to add the area under a curve. So if we look at A here, for example, if we could, we would add up all of the space or the area underneath this. And for B, we would add up all the space under that and so on. But we don't need to do that mathematically. We just have to know what it is. Okay, so here's how this works. If we look at A, there are two types of hydrogen A. There's two types of hydrogen B. And there's 3 for C. Okay, so that's what these relative abundance numbers look like here. That with C, we had 3. And then with B, we had 2. And with A, we have 2. Now, the way that works out is simply that the ratio of 3 C's and 2 B's and 2 A's reduce, right, to 1.5 to 1 to 1. And here's what we do. We took the value for A, there were 2 hydrogens. B, there were 2 hydrogens. And C, we just divide by the smallest one, right? So A would end up being 2 divided by 2 is 1. B would be 2 divided by 2 is 1. And then C is 3 divided by 2 is 1.5. Now, there's one step further. A lot of these proton NMR things will reduce this further. Here's how it works. This now would become the 1, right? This would become the 1. And then this, right, would become 0.66. It will seem a little confusing at first, but it's easier if you actually go back to the original proportions. Now let's remember, carbon C, or hydrogen C rather, had a 3 here, and then this was a 2, and this was a 2. All you have to do is compare them to the highest number. So watch this. Remember, this was a 3, this was a 2, and this was a 2. So for carbon B, you would just take 2 versus 3. That's 2/3, and so that would give you 0.66 for the integration for B. And the same thing would happen here, right? Now, we could do 1 to 1.5, but it's really the same as 2 to 3, okay? We'll see more examples in a moment. These are the integration values for a chloroethane, right? And so we see A, but we should remember that A has 1, 2, 3 neighbors. So 3 plus 1 should give us a quartet. So that's why we have a 4. And for carbon B, B has 1, 2 neighbors plus 1 signal for itself. So that's a triplet. Okay. The relative positions of these is that A, because it's near this electronegative chloride, will be further downfield here. this B, which is a methyl group, further from the chlorine, is not de-shielded, so its magnetic field is somewhat in place. So it would be further upfield or closer to 0. Now what about the integration values? The relative proportion is that there are 2 types of A hydrogens and 3 types of B hydrogens. What you'll see though in lab is when you have a proton NMR reading is that 2 to 3 ratio, right? A 3 to 3 gives you 1, so that's what you would see on your graph or your spectrum. But 2 out of 3 gives you 0.66. So A would be a reading of 0.66, right? 2/3. And then this reading would be 1, which would be, right, 3/3. And by the way, you can see the relative size. If this relative size from this flat part to this flat part is 2, right, then this is relatively 3, right? If you took this 2 and you called this flat part to this flat part as 2, split it in half, right, and you added that up to here, you should get to 3. This is another bromo compound, but this is 2-bromopropane. But notice that it's very symmetrical. So we have 2 A's, a total of 6 hydrogens, but B only has 1 type of hydrogen, but it's still pretty simple. How do we do that? If A here has 6, right, we're going to compare this 1 to the 6. So here B is related to 6 as 0.16, right, 0.16. And so that's what this little guy would be here. And then A would have a value of 1.0 if you look on the spectrum in lab. And by the way, if you multiplied this by 6, right, you would get the same line here, the space between the flat parts. Now, while we don't have the structure for ethanol, this is a proton NMR for ethanol. So you would have CH3, a CH2 in the middle, and then an OH on the bottom. But the relative proportions of these is pretty easy to see, right? You have 1 hydrogen here, 2 hydrogens here, and then a total of 3. But once again, if you have this in lab, proton NMR, you wouldn't necessarily see the 3-to-1 ratio. This would be 1-to-1, right? 3 divided by 3. And so that would be 1.0. This would be 2 divided by the 3. So you'd see a 0.66 here, right? 2/3 is 0.66. And then for this reading, you would get 0.33. So it's really all about the ratios, and it's pretty straightforward there also. Now, let's take a moment to look at the number of peaks, right? We have this type of carbon here, and it's next to a carbon that has 2 hydrogens. So that would be 1 plus 2. So this should be a triplet, a little hard to see. This one here would actually be a quartet. Now you might say, wait a minute, why? Although this carbon is between the oxygen and that carbon, this hydrogen here really doesn't factor into the n+1 calculation. So we're going to disregard that. Okay, so this type of hydrogen gets 1 signal plus these 3. That gives us a quartet. And then oxygen attached to hydrogens, it's a little bit different. So we just get a singlet. This is the last example. And we can see that this is a symmetrical structure, so that A has a twin over here. Okay, so while there are a total of 6 A's, it only gives off 1 signal. Okay, even though there's 2 of them, it only gives off 1 type of signal. So there's a total of 6 A's, there's a total of 4 B's, and then 2 C's. And the integration, or the relative amounts of these, is pretty easy to see. Now, let's take a look at this. This is called tetramethylsilane. It really is our standard. It's what we use for 0. It's a reference point. So you'll learn more about that in college, but this guy is totally full of protons, and so we use that as our 0. Anyway, let's take a look at A. A hydrogens have two neighbors, and so 1 for the A plus this 2 gives us a triplet, right? And it's very far from oxygens, it's far from the double bond, so it's going to be down, it's going to be upfield closer to 0. And then we have this hydrogen B. It is next to a carbon that has 3. So 1 signal for the B plus 3 gives us a quartet. That's right here. But because these are close to that oxygen, it's going to be a bit further downfield. Okay? And finally, when we look at carbon C, right, there are no adjacent hydrogens. Right? There's no hydrogens we can see in the neighborhood. Okay? So that's going to be a singlet. But notice that it's near an oxygen and it's near a double bond. This double bond is pulling electron density away from that. So that's why it's further downfield here. Okay, let's talk about the integration, and then we'll be done. Okay, we have the most of hydrogen A, and that's 6. Right, so we could say the ratio is 6 to 4 to 2. But when you're in lab, it doesn't work out that way. You take this biggest number and you call that 1, right? 6 divided by 6 is 1. For this one, you do 4 divided by 6, which is 2/3. And so that's going to show 0.66. And for this one, you take 2 divided by 6, which is 1/3. And so that would be 0.33. And finally, the integration is shown by the distance between these two flat lines. So if this is a 2, right? If you double that, it should be the size of this one here, right? 2 of these would come up to about here. So you should see that that fits here. 3 of these in size should be about here. Now, I don't quite know why this is the starting line for B. It doesn't matter. So that's the general idea of how we use integration to further understand about the protons in the molecule.